We are going to start with Chapter 12, Intermolecular Forces, Liquids and Solids. And this word intermolecular forces, you should see the word molecular. So that's dealing with molecules made up of only nonmetals. Inter means between molecules, as opposed to intra, which would be within a molecule. So an intramolecular force would be like a covalent bond, whereas intermolecular forces would be forces between two molecules that hold molecules together in the liquid or solid phase. There we go, forces between, not within, molecules. All right, there are three types of intermolecular forces, and you're going to see a list of them, and the list will show up from the weakest to the strongest. So the first one you'll see is the weakest type of intermolecular force. Although you'll learn later on in a more advanced chemistry class, if you ever take one, that this weakest is not actually always the weakest, but it's a simplified model, and that's what you're ready for. Okay, so London dispersion forces are the weakest intermolecular forces. They are also called van der Waals forces. Your book uses dispersion. Many books use London dispersion. Some books use van der Waals, and according to many books, most chemists use van der Waals forces. So you have to be able to use these terms interchangeably. If you see van der Waals forces, you should think dispersion. If you see dispersion or London dispersion, you should think van der Waals. Both intermolecular forces. All right. All molecules experience London dispersion forces or van der Waals forces. Van der Waals forces. What are these dispersion forces? What does that mean? They are forces that are caused by temporary dipoles in a single molecule. So a single molecule might have a temporary dipole, and I'll explain in a minute how that happens. And these temporary dipoles induce temporary dipoles in neighboring molecules. So sometimes what happens is electrons in one molecule will move to one side or the other of that molecule, and that creates a negative and a positive end, which would be a temporary dipole, because if you have a negative and positive end, you have a dipole. It's only temporary because the electrons might go back to where they were. All right. Now, these London dispersion forces, they increase with the number of electrons in a molecule. And one of the important things to note, because students often do this wrong, it's your total electrons, not valence electrons. We've been doing Lewis structures, and you're getting very used to counting valence electrons. So many students mistakenly only count the valence electrons to determine London dispersion forces strength. You want to count the total number of electrons if you're comparing the strength of London dispersion forces between two molecules. All right. If you're comparing which molecule has stronger London dispersion forces, the molecule with more total electrons will have stronger London dispersion forces. And the reason is that the more electrons you have, the more easy it is to become polarized. Now this word polarized, that's just having a dipole. If you become polarized, it's because your electrons move to one side of the molecule, making a negative part of the molecule, and the opposite side would become positive, hence becoming a dipole, temporary. And that means the molecule has become polarized, which just means to have a positive and negative end. So the more electrons you have, the more easily polarized you are. In addition to just total number of electrons, a molecule can also have stronger dispersion forces if it's a more complex, longer molecule. So the shape of the molecule also affects London dispersion forces. Okay, so now we're going to look at an animation of these London dispersion forces. Actually, we're not going to do that yet. But if you ever want to look at the animation that I'm going to show you in a moment, you can always go to this website. But before I show you the website, I just want to show you, we're going to do a visualization of what these are before we look at the movie of what they are. Okay, so here we have a helium atom. And this positive charge on one helium atom, it's the nucleus of the helium. It's got a +2 charge. And there's 2 electrons in there, so overall this whole thing is neutral. But these electrons might be slightly attracted to this +2 because this electron right here might move over to the other side just randomly as it's moving around. So this electron right here and this electron right here in a separate helium atom might get attracted to this positive nucleus. And notice now the electrons are over on the left side of this helium atom, leaving this side of the helium atom with no electrons. So suddenly this side becomes slightly positive because there's no electrons there. This side becomes slightly negative because both electrons are on this side. And now this helium atom, which should be nonpolar, has a sudden dipole, negative, positive. So now let's suppose this atom right here is this, is this atom. Oops, no wait, actually we could say that this atom is this atom right here. So suddenly the helium atom on the right, which was this atom, has this dipole, and this helium atom is going to induce a dipole on this atom because these electrons are negative. They were over on the left side of the atom. So there's a slight negative, which pushes away the electrons that were in this atom and sends the electrons over to the other side. Okay, so these 2 electrons get sent to the left side of this atom. So now there's a slight positive charge over here and negative charge over here because the electrons in this atom, not connected or bonded to this helium atom, but these electrons have a slight negative, the delta minus, and they push the electron of an adjacent atom over to the other side. They repel those electrons, and this atom now has a slight positive charge right here and a slight negative charge over here. So what happens is this atom gets a temporary dipole, and it induces a dipole onto this atom, which will then induce a dipole on its neighbor, and on this neighbor, and on the next neighbor. And now we will watch a video to see what this looks like. Okay, so here are a bunch of atoms, or they could be molecules. They're just represented by balls. And so this would be a symmetric type of atom or molecule. They're nonpolar particles. So this would be in the solid phase or the liquid phase. The liquid phase, the difference between liquid and solid is, you know, the liquid particles can move around. In the solid, these are stuck in space, but they still move a little bit. So this would be a solid. And solid particles, even when you're in the solid, the molecules or the atoms, they still vibrate left, right, up, down, around in circles. They're still in this space in here. Okay. So first we're going to look at the electron density. So normally electrons are randomly distributed around each atom. So this is showing a random distribution of all the electrons. The red dots are the electrons. And now this atom right here, or the molecule right here, is going to have a temporary dipole. And this is what that would look like. Notice more electrons are down at the bottom, fewer electrons are up on top. So that atom or molecule has a slight positive charge up on top and negative charge down on the bottom. Now what's going to happen is this atom is going to induce a dipole on its neighbor right here. And what do you think this side will be? Are the electrons in this atom going to be pushed up or down by this positive? Is the positive going to attract electrons or repel electrons? Think about it. And think about what's going to happen in all these neighboring atoms and how this one temporary dipole is going to induce dipoles on all the neighbors. So here you go. What happens? Well, this one induces a lot of dipoles on all its neighbors. And notice the positive brings the electrons down toward here, so this becomes negative. This becomes positive. Over on this side, this positive part of the atom or molecule attracts the electrons right here and here. So this edge of the atom over on the right, this top part becomes negative and negative. And the negative on the original temporary dipole induces a dipole on this neighbor and this neighbor and this neighbor. And these induce dipoles on their neighbors, and all of a sudden everything has a temporary dipole. So now, That was a shot in time. Now let's watch what this looks like just over time. This is what London forces look like. Up, temporary dipole, induced temporary dipoles. They all go away. Oops, temporary dipole, induced temporary dipoles, one away. Oh, temporary dipole, induced, one away, induced, one away. Oh, one over here, induced, one away. Oh, over here, induced, one away. They just keep coming and going. They are temporary dipoles. That's a very important concept, that we have these temporary induced dipoles, and it's what keep these together in the solid phase. If London dispersion forces did not exist, then nonpolar molecules and atoms could never be in the solid phase, because there would be nothing attracting them to each other. They would always remain gas molecules. They would never go to the liquid phase because nothing would attract them to hold them next to each other. It's these London dispersion forces that keep the molecules together when they go from the gas to the liquid phase and then the liquid to the solid phase. Okay, enough on London dispersion forces. Those are the weakest forces. Non-polar molecules and polar molecules all have London dispersion forces. Everything has London dispersion forces. Now we're going to go to a stronger force, dipole-dipole forces. These are forces between molecules that are dipoles. And they have actual, not temporary dipoles, but constant dipoles. They're not temporary, they are always present because the molecule is polar, so it has a positive and a negative end. So only polar molecules have dipole-dipole forces. They're caused by the positive end of one molecule lining up with the negative end of a neighboring molecule. And the positive end of one molecule is attracted to the negative end of another molecule. So there's an attraction between the positive and the negative end of two neighboring molecules. And we'll see a movie in a minute, but first, let's look at what this looks like. Okay, so over on the left side, we've got 6 hydrochloric acid molecules, or actually, yeah, hydrochloric acid molecules. And you see the dipole charges, the negative and the positive end. The H end of HCl is positive. The Cl end of an HCl molecule is negative. So we've got a bunch of HCl molecules. These red lines over on the right side are showing you the dipole forces between molecules. So the positive end, here's an HCl molecule, here's the positive end, is attracted to the negative end of this HCl molecule. So I've drawn in all the different places where you can have attraction between positive and negative ends. All these red dashed lines, those are the attractive forces, the dipole-dipole forces between HCl molecules. Okay, it's very important to note that the bond, these little dashed lines here, the dash, these dashes are your covalent bonds. That's what's holding the H to the Cl. The red dashes are what's holding one HCl next to another HCl in the liquid or solid phase. So I've already pretty much explained dipole-dipole attractive forces, but I'm going to show you a quick video. Click the mouse. So here's one dipole, here's another dipole, and they are in the gas phase and they see each other and they're like, oh, I'm kind of attracted to you. I've got a positive and a negative end, and you have a positive and negative end, and my negative end is going to be attracted to your positive end. So these were in the gas phase. They come near each other and watch what happens. Okay. They are going to, we're just showing you where the positive and negative ends are. Now this negative end, when it gets near this positive end, it's like, ooh, I see you, I'm attracted to you, and they line up, and now these two molecules, if their temperature is low enough, there's going to be a dipole-dipole attractive force between these, whether or not the temperature is low enough. There's always this dipole-dipole attraction if these molecules get close enough. And if the temperatures are low enough, they will actually not keep moving on, or I shouldn't say temperature. If the molecules themselves don't have enough energy, they will then bind together through these attractive forces. It's not a molecule, the two together, but they can suddenly form a liquid droplet if enough of these molecules come together. Okay? So now we're going to see the whole thing. Gas molecules moving around randomly. They have positive and negative ends, and they randomly bump into each other, and they notice each other, and they line up, and now they are attracted to each other and sort of stuck together. All right, the next force, the last one for intermolecular forces, very important, intermolecular forces. The last force we're going to look at is hydrogen bonding. This is the strongest intermolecular force. It's a very strong dipole-dipole force. Okay, hydrogen bonding only happens in molecules that have nitrogen, oxygen, or fluorine bonded to hydrogen. It's very important. Hydrogen bonding is not within a molecule, it's between two molecules. It's very easy to confuse hydrogen bonding, so I'm going to show you a bunch of models of it. So, one molecule with NO or F bonded to H can hydrogen bond with any other molecule that has NO or F in it. So two different molecules can have hydrogen bonding with each other. They don't have to be the same exact molecule. When we say hydrogen bond, we're not talking about a covalent bond. Electrons are not shared. These hydrogen bonds have about 10% the strength of a single covalent bond. And this is so important, this piece right here, very important. Hydrogen bond occurs between an H bonded to an NO or F in one molecule and the lone pairs on the NO or F in a separate molecule. So, let's see a picture. All right, here we go. Ignore this piece down here. Just ignore that for now. That's another picture. So we have water molecules. The little gray things are the actual covalent bonds. The blue dots are the hydrogen bonds. So here on the right side, we have 1, 2, 3, 4, 5, 6, 7 water molecules. So here's a water molecule, and this is showing you a hydrogen bond between this molecule of water and this molecule of water. There's a hydrogen bond. Between this molecule of water and this molecule of water, there's a hydrogen bond. Notice the hydrogen bond is between the H on this molecule, and it's going to the lone pairs on the O of this molecule. This O right here, that O has lone pairs, and this H atom is very attracted to those lone pairs on the O atom. Okay, now this next picture is just showing the difference between the covalent bond and the hydrogen bond. So the covalent bond is right within a single molecule. All right, you understand that hopefully? So here's our oxygen atom. This is a hydrogen right here. This is another hydrogen. These are the lone pairs. All the negatives are showing you where the electrons are in bonds, covalent bond, or lone pairs. There's a lone pair right here, so we see the negative. That's the lone pair on the oxygen. There's another lone pair on the oxygen. Here's the covalent bond to the H atom, and another covalent bond to an H atom. So here's a covalent bond. Now, here's one water molecule, here's another. The hydrogen bond right here is between the two molecules, and the hydrogen bond occurs between the hydrogen atom, here's hydrogen, and that hydrogen bonds to the lone pairs of this oxygen atom. It's always between hydrogen and lone pairs on an N, O, or F. Extremely important. Okay, this next picture is showing you that hydrogen bonding doesn't only occur between like molecules. This water molecule can hydrogen bond to an ammonia molecule. The H on the water, the H has to be bonded to an NO or F, and notice this H is bonded to O. Okay, so this H is capable of hydrogen bonding. It will hydrogen bond to any NO or F on any other molecule. Well, here's another molecule. It's separate, totally separate molecule. There's a nitrogen, and here, right here, is our hydrogen bond. So the H is hydrogen bonding to a lone pair of this N. Last example for hydrogen bonding. I'm emphasizing a lot on, I'm emphasizing what a hydrogen bond is, because so many students confuse what hydrogen bonds are. They think these covalent bonds between the H and the O in a single molecule is a hydrogen bond. It is not. This right here is a covalent bond. These between the atoms, between two separate particles. This right here, those are the hydrogen bonds. So here I've got a sulfate ion, and you can hydrogen bond between a molecule and an ion. So This water molecule is hydrogen bonding to the oxygen of the sulfate molecule, because this oxygen has lone pairs. This oxygen has lone pairs. Notice, this sulfate molecule is not itself capable of creating a hydrogen bond because it has no hydrogens. But it can hydrogen bond with a molecule that has H bonded to NO or F, O right here. And these H's on water can hydrogen bond to any NO or F, like this N right here or this O right here, on any separate particle. Okay, hope that all makes sense. And here is your summary of these 3 types of intermolecular forces. There's your summary. Okay. I'm not going to read it out loud. Everything has already been said. Strongest to weakest, strongest hydrogen bond, weakest London dispersion forces. So let's do some problems. We're going to identify the types of intermolecular forces present in each molecule. So first we're going to do F2. Normally you would have to draw the Lewis structure. And it's through the Lewis structure that we find out if we have a polar or nonpolar molecule. However, since we have F2, it's F bonded to F, and we know that that is not even a polar bond, and we only have one bond. Therefore, this thing is nonpolar. And if you're nonpolar, you can't have hydrogen bonding. There's no hydrogen in here. You're nonpolar, you cannot have dipole-dipole bonds. The only thing you can have is London dispersion forces, because all molecules have London dispersion forces. So I just wrote what I already said. Okay. On to HCl. So this time, again, normally you would have to draw your Lewis structure. When you have only 2 atoms, you don't have to draw the Lewis structure at all. You just have to check the electronegativity difference. If the difference in electronegativity between the 2 atoms is greater than 0.4, you know that you have a polar bond. And if there's only 2 atoms, there's only one bond. If the bond's polar, the whole molecule is polar. So we know HCl is polar. It therefore has dipole-dipole forces. All molecules have London dispersion forces, so this also has London dispersion forces. Now we have to check hydrogen bonding. Well, we have an H, but the H has to be bonded to NO or F. Cl is not NO or F, so this does not have hydrogen bonding. There you go. HCl has only London dispersion and dipole-dipole forces. All right, next molecule, SO2. You actually need to draw the Lewis structure. So I would like you to draw your Lewis structure. You're going to pause right now. When you unpause, I'm going to have the structure and the polarity, whether or not the molecule is polar. You have to put it in its correct geometry, add the bond dipoles. That will all be shown to you. Hopefully you're pausing. It's all going to show in a moment. There you go. Hopefully you figured this out. We've got our SO2 molecule. You have to always do the Lewis structure first. Then you have to figure out the molecule's geometry, add up your bond dipoles. You didn't start and end in the same place, so these do not add up to 0. Therefore, the molecule is polar. Since the bond dipoles do not cancel out, SO2 is polar and has dipole-dipole forces. And it also has London dispersion or van der Waals forces, because all molecules have van der Waals forces. Oh, does it have hydrogen bonding? Well, there's no hydrogen in here, so no, it doesn't have hydrogen bonding. All right, NH3. Again, go ahead, do your whole Lewis structure, your geometry, see if it's polar. You'll see the answer in a minute. Go ahead and pause, because I'm about to show the answers. Okay, Lewis structure, molecular geometry, trigonal pyramidal. We add up the bond dipoles. They do not start and end at the same place, so this does not equal 0. So NH3 is polar. Okay, so we know NH3 has dipole-dipole forces. It has H bonded to N. Therefore, these H's can hydrogen bond to another NH3 molecule. And I will draw that for you in a moment. But before I draw that, you just want to see, so that NH3 can have hydrogen bonding with other NH3 molecules. And again, I'll show that to you in a moment. And NH3 also has London dispersion forces, because everything has London dispersion forces. All molecules have London dispersion forces. Okay, so I just drew, this is an H over here. I just drew another NH3 molecule over here. This one is not in its actual correct form, but that's okay. This H from this ammonia molecule is hydrogen bonding. The green is the hydrogen bond. It's hydrogen bonding to this ammonia molecule that is a separate molecule. And notice the hydrogen bond is between the H in this ammonia and the lone pairs on the N of this separate ammonia molecule. And this little hydrogen bond here is not a covalent bond. It's about 10% the strength of a covalent bond, but it is not a covalent bond. I'm hoping I just recorded that section. I'm pretty sure I did. Okay, another example, N2. Try to do that on your own. I'm about to show you the answer. So pause. Answer's coming. Pause. Here's your answer. N2 only has N bonded to N. Molecule's not even polar. We don't have to check. Only has London dispersion forces. Okay. Rank fluorine, hydrochloric acid, ammonia, and nitrogen from strongest to weakest intermolecular forces. Now you can choose to pause or you can just see the answer, but I'm about to show you the answer. Here we go. Okay. NH3, strongest because it has hydrogen bonding, which you were told is the strongest type of force. Now, N2 and F2 are nonpolar, so they're definitely not the strongest. HCl is the next strongest because it's polar. It has dipole-dipole forces. Now, between N2 and F2, if you didn't pause, go back and read the whole thing. N2 and F2, you have to check total electrons, so you see which one has more electrons, and you can pause this for a minute, count them yourselves, or just see what I wrote. So N2 and F2, you check the total electrons. Total, not valence. F2 has 18, N2 has only 14, therefore F2 has stronger dispersion forces, and N2 has the weakest forces of the four molecules.